I'm going to introduce a thing called Zoe, and I'll tell you where it exists as we go through this in the Agoric stack. First, I have a question. How many people here have actually interacted with a smart contract? So about half the audience. I think the other half of you are lying, but we'll talk about that in a moment. So let's see, did it move? Oh, so the problem here is this is not actually moved. There we go. Oh, now I wonder if it'll work. So I'm going to talk about the background. I'll tell you a little bit about Zoe. I will talk about the electronic rights transfer protocol that is behind that in our platform, and then wrap it up, just so you see where we're going. Yes, it worked. OK, so we've been working on smart contracts. I worked on the first production smart contract back in 1989. So in case you aren't doing the math yet with this lovely liquor here, that was before blockchain. And so that is a contract-like expression in code where the execution of the code enforces the terms of the contract. So it controls the rights transfer. It controls the conclusion. It controls the parts of a company that could be made operational, that could be made precise and objective. And so a lot of people can think, OK, so Bitcoin is actually a smart contract. Right? It's code that is arranging the coordination between multiple third parties to move money back and forth. But we were working on this 30 years ago, so what happened since? Well, I can go to a website, put in a bid for an article, it automatically processes. If I win the auction, it automatically pays the person who put up the goods, and the money transfers. There's automated dispute resolution. That sounds like a smart contract. It is, however, called eBay. eBay, Venmo, PayPal, much of Lyft and Uber, much of Amazon, all of those are software systems where most of the actual execution of rights and actual execution of contract-like behavior between independent third parties that are not at the company is orchestrated by software. And so smart contracts have already happened. There's already hundreds of billions of dollars of market cap in smart contracts. And so now, of course, I'll ask again of the people who have said no before, how many of you have talked to a smart contract? And no one bought anything for Amazon? OK, good. OK, so if smart contracts are already successful, where do blockchains come in? What do they do for us? So from my perspective, right, a blockchain is multiple independent computers agreeing on things. Well, the independent computers, where that means different administrative zones, different jurisdictions, so that there's no administrative single point of failure, shall we say. And they have to agree on things. So they vote to agree on data. Well, that's easy. That's just sort of timestamp this stuff. But harder is vote to agree on choices. I took this money and I gave it to Dave, not Alice. And that's what requires consensus. That's where blockchains really brought new technology to the system. And finally, they agree on the results of computation. And that's where smart contracts come in. And so what the net result is instead of having to do our smart contracts with a trusted third party like eBay or PayPal or Venmo or whoever, I can instead have a high-integrity, neutral third party, trustless third party, pick your term, but it's a platform that I can rely upon to execute correctly. So now I can directly engage in contract-like behavior with total strangers, executing code that I rely on the correct execution of. And that's nice. That's a new ability to express software and have it enable cooperation. So we've been building a platform up from this. And remember, we did smart contracts before there were blockchains. So from my perspective, blockchains essentially introduce a new kind of computer made from agreement rather than silicon. So we did cryptographic protocols between machines. Now some of those machines happen to be replicated across the globe. And there's protocols to do that, but it's still coordination among independent machines. Above that, we build a computational layer of simple, sequential, transactional units of computation that normal programmers can understand. It's familiar from Node.js or browser programming, what have you. embedded in a world of asynchronous communication, right? The world out there is asynchronous. There's events all around. And so that asynchronous communication, we actually have a joint project with Interchain Foundation and All in Bits to build inter-blockchain communication protocol, which is a consensus-neutral, platform-neutral communication protocol between blockchains, between machines and blockchains. And so we layer on top of that, that connects our independent units of computation, which we call VATs. And on top of that, we build an execution model. For us, it's in JavaScript, but the general architecture applies to multiple languages. I'm pretty sure there's someone here who would like it in Rust. And that's stitched together using a protocol we call CAPTP. So that's a remote invocation, remote object protocol that just gets marshaled onto the underlying IBC data channels. And because IBC handles all of the relay between blockchains and agreement on consensus and all the details of transport, authentication, and ordering, we can just layer on top of that the same way we would layer on top of TCP. And so we do marshalling of messages between machines. And so what that means is I can have, I've got a lightsaber here. I can have does my lightsaber work? Yes, there we go. You can see the little green dot. Can you see the little green dot there? Great. So I can have an object in one VAT on one machine, send a message to an object on another VAT on another machine. It's just an asynchronous message. It doesn't know whether the VAT is local, whether the VAT is on the same chain, whether the VAT is on a different chain and it took IBC and inter-blockchain communication to cross the bridge, to cross that boundary, whether it's on a private chain, a private machine, etc. It's just an async message, and eventually the answer will come back. And those different technologies just affect what the latency is of that response. Okay, and then above that, now we're at the object level. Now we're programming in JavaScript. You saw JavaScript on the screen before. And so above that, we then build objects that let us easily express contract-like behavior. So escrow agents, auctions, futures, forwards, etc. Those kinds of things you can build as JavaScript objects only because they can reach out over the network to other machines or contracts on other machines. That auction on one machine can be auctioning off a concert ticket that's hosted on another machine. And when I say another machine, I mean another chain or a private chain or what have you. Okay, so that gets us to contracts, and to do that, we have a protocol called Electronic Rights Transfer Protocol, and I'll talk some about that in a minute. But that gives us the ability to abstract across how we do exclusive transfer of rights, transfer of ownership, confirmation of the quality of an item, all those kinds of things. And I'll talk a little bit about each of those. But what we're doing tonight, what I'll introduce tonight first, is what we call Zoe. When we went out and started plotting, building the stack, we came up with this idea and we realized it would be very exciting, but we wanted to, nucleate it for a while, and so we haven't talked about it outside. And so I'm talking about it essentially for the first time here tonight as something we've articulated occasionally as secret sauce that we intend to be in our smart contract framework. And so that gives us what we consider to be a better model for doing smart contracts. So before I quite dive in, a little bit more background. So several people here have worked with smart contracts. What's wrong with this picture? And don't say it's MetaMask, because they're doing some really awesome stuff with our security technology. What's wrong with it is that the user here, which thankfully is another face of Dan, is sending a bunch of money to essentially a random number. And hopefully that random number is a friend of yours, but while I've been random, I'm usually not a number, so that interface scares me. It's very low level. And it's not just MetaMask. It's pretty much all the platforms, right? That's the Looney wallet for Cosmos. You see the same thing in all the other platforms. And it's not just payments. It's also the applications. This is Uniswap on the left. I'm putting together a trade which might be for a lot of money, and I'm saying pay it. And what am I paying? Well, at the end of the day in these applications, I'm paying a random number. I'm going to send my money to the other end of some chain, and hopefully software runs that does what I expect. And some point in some address that I hopefully have control of, assuming I didn't get my random number wrong, a bunch of different money appears, and maybe I discover that, right? It's a very low-level, very fragile experience that we're cobbling together to get a blockchain experience. So So let's talk about a different way of doing that. The thing is, that's very one way. I send money, maybe something happens, maybe I get something back. But contracts are about the cooperation of multiple parties. It's not that I just want to throw money over the fence, it's that I want to spend some money for a quid pro quo. Right? I'm not sending you money, I want to buy a concert ticket. And if I'm not going to get my concert ticket, then I don't want to give you the money. Right? And so this is a Uniswap variant that we built, where, same expression, only of course the money is coming from purses that are named, so I don't just have a pile of Ether, I've got my business account or my operating account or what have you. And when I say pay, I don't get, here, send some money to a random number, I get an offer. An offer is multiple parts. It's what am I offering? What are the goods I'm willing to pay? And what do I expect to get from that? What do I want to get out of this exchange? And so that offer is, pay 3,000 moolah from my savings account, and I expect to receive 2,000 simoleon into my marketing account, okay, or purse as we call them. That's a much safer interaction as long as it's enforced. As long as I'm actually protected, so saying my offer this way actually buys me something from a safety point of view. So, thus we have Zoe. We're at testnet now, we have a proof of concept, people start hacking on it, so you can't rely on it yet, but we're getting there. So what does it do? So Zoe, it's about using offers everywhere, and they show up in a bunch of places. You already saw it in the user interface. I just saw that screen back there with two people talking to each other. It's like, wait, why are they talking to? Anyway, so let's say I want to sell that concert ticket. The seller, in an auction, it's not that the guy with the concert ticket is the auctioneer or necessarily is running the auction. They just want to sell it in an auction. So in some sense, they're a customer of the auction as well. So they create an offer that says, yeah, I'm willing to sell my concert ticket, but I need to make at least this much money. I need to make at least X moolah for this concert ticket. Think of that as the reserve on their auction, right? And now a bidder comes in. What does a bidder do? Well, a bidder wants to pay at most Y moolah in exchange for a concert ticket. And by gosh, they better get that concert ticket, or they better get their money back. That's what they're expecting. And so Zoe, an important thing here, and this is what Zoe provides, is what we call pervasive escrow, right? It's not that the Y moolah that the user is bidding goes to the auctioneer, and then you hope the auctioneer is honest, and you hope that if you lose the auction, they give it back, which is what you see in typical smart contracts on other platforms. It's instead, those assets go into Zoe, and Zoe escrows them, and then securely notifies the auction that, hey, there is a legitimate offer with real assets for Y moolah to get that concert ticket. So now the auctioneer's code is much simpler. It doesn't have any of the money handling. And it just figures out, here's how I'm going to, of all the offers present, where the two offers of import right now are the highest bidder for a concert ticket that wants to give the most moolah, and the person with a concert ticket that is trying to get moolah, right? And those two offers are compatible, and so now Zoe does a rearrangement that says, it is consistent with the constraints that all of you have provided, that I take the concert ticket from him and give it to him, I take the moolah from him and give it to him, right? So that now the seller will get moolah and the highest bidder will get the concert ticket. And Zoe will allow the auction to specify that reallocation. It will check a couple of key properties. The first is that all of those offer constraints are met, which is to say I'm not charging the bidder more moolah than they were willing to pay, and I'm paying the auctioneer at least as much as he required to fork over the concert ticket. And if that happens, then Zoe will cause the reallocation to happen. And it'll also, before I go there, it'll also make sure that of the reallocation, of course, currency is conserved, right? So assets are conserved. I can't manufacture moolah out of whole cloth. That would be shocking, right? And so Zoe enforces that on a continuing basis. And so it does a transfer. And finally, it exits, and Zoe provides the rewards to all of the parties. So the winnings to the winning bidder, the refunds to all of the bidders that put money in that was escrowed in Zoe, but they didn't win it. And the important characteristic there is their offer said that they need a concert ticket before any of their money gets forked over to the seller. And so there is absolutely nothing that the auctioneer can do, there's nothing that the seller can do in order to get the money from a losing bidder. The only way they can get the money is to provide another concert ticket that Zoe recognizes as the thing that was required by those bidders. And so you have this safety property that we call offer safety. Now, software engineering is a history of improving safety properties, right? Type safety, memory safety, concurrency safety, and they didn't magically make all the bugs go away. But for each of those categories, they really did take 80% of them off the table, right? Once you had memory safety, suddenly, all of those random pointer writes or walking off into memory or buffer overflows, they just went away, right? They were just gone. It wasn't that they suddenly turned into some different hard problem. No, they were just gone. Now, there were still 20% of the bugs left, and those are hard bugs, but they were already there. But taking 80% off the table, awesome. And so this is a safety property. Now, I have this separation of concerns. Well, the guarantee I provide to the clients, right, is that either they will get their desired payout, they will get the thing they wanted, or they will get a refund. And they're, one of the two. And I'll talk a little later about how they might get both. But they get that regardless of the behavior of the contract. They get that even if the contract gets upgraded in the middle of this execution. Even if the contract is compromised, even if the contract is buggy, they get the asset they wanted or the refund. And having that be pervasive throughout the architecture of a smart contract platform, that seems to me like a significant step forward in the safety that we provide all of the clients if we want millions and millions or billions of users on these platforms. But it also gives guarantees to the servers, to the contracts, which is to say, the contracts don't get the money directly. They don't have to worry about dropping it or returning it or accidentally having someone steal it, so suddenly they owe people money that they don't have. What they get is offers where they have platform assurance that the asset the offer is describing is synchronously available, right? That the contract execution can do a reallocation synchronously and it just works. And that turns out to be really nice. It simplifies the architecture of those code. And they get the assurance that the assets will be delivered on completion, that they won't wander away, that there won't be a failure or a library gets removed, so now those assets are permanently locked up and you have to keep struggling to get them out. And so those assurances are hugely important to the contract implementers and simplify the implementation of these contracts. So in March of 2018, there was a paper about, and this was one of the inspirations as we were chewing on, gee, these things shouldn't be possible. It was a study with static analysis of a bunch of Ethereum contracts that identified 34,200, I think, of these contracts that looked like they had one of these three vulnerabilities. Greedy being, that the money might go in and never come out. Prodigable meaning that some random person might come along and take the money. And suicidal meaning they might turf in such a way, or someone outside could say, yep, you're done. And now all the assets they had are locked up. And continual assets coming in, yeah, they get locked up and stuck there. And those are all bad, right? And those are all properties that should simply systemically not be possible, right? You would like in writing a smart contract that these are not things that are a problem. You would like, as a user of a smart contract, to not be concerned about them. So offer safety addresses several of these. But it's not a complete solution, right? So offer safety clearly addresses prodigal because, the bad code can't get my money unless it provides me what I want. And now I don't care what it does with the money. I got what I want, right? As a client. The other is greedy. You can get something stuck. So there's another safety property, right? Once we identified offer safety as a thing, we generalize that to what we call market safety properties. Properties that make it safer, that do the same kind of thing that memory safety did, that make it safer to participate and build a market, right? So exit safety, right? And the first element of exit safety is, of course, the contract at any time getting an offer can simply say, yeah, not enough money. Or you won it too soon, nope, I'm going to eject that offer, I'm done, right? So from the contract's perspective, they can refuse any offer. But what guarantees do the clients have? Great, I put my offer in. If it's satisfied, I will get what I want. if it exits, I will get a refund of everything I put in. What if they just sit there, right? And it turns out there's, well, depending on the price of Ether, there's hundreds of millions of dollars just sitting there in a few contracts that are stuck, right? So we have exit rules, which are all about who can terminate a particular offer. Multiple offers go into a contract. Who can terminate? So I'll give you several of the rules that are currently supported in the proof of concept. On demand means the offer's there until the client says, yeah, give me that back. And that's a race, right? The contract might be busy trying to take your offer and provide you the goods on the other side. So it is a race, but back to what you want architectural assurance of, it is not possible in the architecture of Zoe for the contract code that you don't necessarily trust, because it might be that you are doing business with, an interesting business that someone you met on the street recommended to you. And it needs to be the case that that cannot obstruct you requesting Zoe to return your offer and the offered goods being refunded to you. And so that's architecturally a property, even if the contract doesn't want to, even if the contract goes into an infinite loop. Yeah. Deadline, right? So you want to have offers that it's not on demand. I can't do a covered call that will be valid until next Thursday unless I can actually lock up the assets you're going to offer until next Thursday. But after next Thursday, you can get them back. Now, maybe that's automatic, maybe that's on demand after next Thursday, but you've got to be able to specify times in order to do subscriptions, forwards, futures, all these kinds of things. Or not forwards, but futures. Yeah. And so our system supports having deadlines with respect to a time reference. Might be block height, it might be the time on the long now clock, as long as it is an agreed reference that the contract and the participants in the contract understand and can agree on, right? That's what you require. And then obviously there's some that are very easy, very fast, very simple, but fundamentally, particularly in a world of cross-chain cooperation, distributed across multiple machines, I might, on a chain over here, be using as a reference the block height of that chain over there. Right? So it's not my local block height, it's some interesting thing over there because I migrated my contract, or because that's where the market is for the covered call that I'm trying to sell. And then finally there's the, yeah, it's up to the contract, right? I can request as a client to get my offer back, but it's entirely up to the contract whether it does so, and I've read the code, and it's got a policy, and I like it, great, that's fine. So there's various, but the most important one is one you get automatically, and of course it's the one that we haven't yet implemented but we know how to, which is on failure, right? If there's any critical failure of the contract, it turfs, it divides by zeros, it has uses too much resources, infinite loops, whatever. Well, that failure means that the infrastructure can detect it, and all of the offers, they're just instantly rejected, they're instantly ejected, everyone gets a refund, we go home, and everyone's happy. Or at least all the clients are happy because they got offer safety. They got offer safety executed right now when there was a failure, and they didn't get stuck in a limbo. Okay, so now we can say a little bit more about the detail of these things. And I must apologize, I have if anyone's seen earlier talks in this series where Markham has done his absolutely fabulous animations all over the place, most of my animation is in my wildly waving hands, and at best you get the fade-ins in, right? So, okay, so how does this work? So, as a client, my wallet, not me, so this is just code, but as a client, I'll construct an offer by providing what I'm willing to offer, a description of it, what I want for that, the concert ticket, an exit rule by Thursday, or whenever I ask, right? The on-demand rule, and a payment that actually provides the assets I said I was willing to pay. I said I'd pay 4 moolah. I'd better have the 4 moolah in a payment that goes to Zoe and gets escrowed. And then and what I get for that is I hand that off to Zoe with the description of here's the 4 quatlus, here's what I'm willing to let those go for, otherwise you have to return them to me. And what I get back from that is a receipt for that, the escrow receipt, and a promise. If you're familiar in JavaScript or various other languages, there's a asynchronous model of computation that, in fact, Mark and I invented for com stuff back way too many years ago. And so I get a promise for the eventual payout, either my refund or the winnings. And once I've got that escrow receipt, that's what I pass to the contract. So I'm passing to the contract an object that proves that it can verify represents control over the ability to the assets and the offer that I have registered with Zoe. And on completion, that payout promise that I got from Zoe, so I got it from a trusted path in exchange for the goods that I provided, it will resolve to being my winnings or my refund. I mentioned earlier that maybe I get both. In the auction case, I might have said pay at most 40 quatlus. And if it only cost 20 because it's an auction and there was no other bidders or that was the bid, well, I'm going to get the concert ticket and 20 of my quatlus back. So that's not the full refund case where I got ejected without satisfaction. I got a successful offer, I got some winnings, and I also got a refund. And the refund comes on essentially the same path. So it's a nice, simple compositional system. The abstractions are fairly simple, but they're incredibly powerful. The process is extremely powerful. It provides this pervasive protections throughout. So, you know, one last round of things. So the operations that Zoe, the framework, provides to the clients, to the people outside, or the programs outside of the smart contract, are a trusted path to contracts, right? You know, I want to get not to a random object on the other end that really promises it's Uniswap. No, really. I want to talk to a trusted agent, the Zoe, and say, here's the contract that I need to connect to. So it provides that trusted path, and it provides a trusted way to go. And what source code is it running? You know, on Ethereum or some of these other chains, if I know the address, i.e. another random number, I can go look it up and I can see that that random number corresponds to some code, and hopefully that's the random number I send my money to. But A, that's not very satisfying, it's not very user-friendly, and it doesn't work well unless you're on a public chain and everything's obvious. Our architecture spans public, consortium, and private chains, individual machines, you know, my phone, everything else. And so you need a model that works across those platforms. Well, you ask Zoe, here's the contract I'm trying to do business with. What software are you running for it, right? You're the platform it's executing on. Tell me what it'll actually do. And then finally, Zoe is the one when I got that escrow receipt, I also got the ability to exit. And so I'm not going to ask the contract to exit. I'm going to ask Zoe saying, yeah, that contract, you know, that offer I gave you, yeah, give it back. I want out. And it will interact with the contract so the contract knows it, but the contract isn't allowed to obstruct my exit. And then finally, of course, Zoe provides the payouts once I exit. Huge, so that's what it provides to the clients. For contracts, this is on the inside. Now I'm on the inside, I'm running on top of Zoe. So the key thing is, of course, I got running on top of Zoe by instantiating myself there, so there's a mechanism to be able to deploy and instantiate contracts in Zoe. So it's a contract runtime API, if you will. And it notifies me, it lets me react to new offers that are available. And remember, these are offers where the assets are synchronously available. So I'm in an asynchronous world, but I can synchronously interact with all the offers and assets that I'm supposed to compute in terms of. And finally, it supports the reallocate operation that preserves currency, conserves currency, and ensures the constraints of the offers are honored. So there's a few nice side effects of this model. At Osaka, a couple people reported to me at the DevCon that people were starting to get concerned about how asynchronous the world looked, right? The simple smart contract models were simple, deterministic, synchronous machines that you know, had reentrancy bugs, but hey, it's simple. And that was nice. The problem is the world is not that nice. The world is an asynchronous place, right? So sharding brings up asynchrony. Cross-chain communication brings up asynchrony. Games and handling events and high-frequency machines bring up asynchrony. Oracles bring up asynchrony. All these things add asynchrony to the system, and this was making people concerned because the simple model of the world was starting to creak. One of the nice things about this is that when an offer is presented to Zoe, it handles the escrowing asynchronously, right? Our infrastructure is entirely async, so it can span multiple machines and so forth. And so that whole process of saying, you know, here's 4 quatlus, where 4 quatlus is actually a tier 2 token implemented on that chain over there, so it might take some negotiation to get it all escrowed carefully. But once that's done, my offer goes in. And so from the contract's perspective, it just gets synchronous access to the offers, as I mentioned. But so all the data is escrowed by Zoe, and then the notification happens to the contract. So as far as the contract's concerned, it's just living in a simple synchronous world. It's insulated from some of the async vagaries of the rest of the world. And then finally, as a result, one of the nice consequences out of this is that we get uniform handling of tier 1, base tokens on the platform you're running on, tier 1, tier 2, sorry, layer 1, layer 2, synthesized tokens equivalent of ERC 20 or ERC 721, and off-chain assets. So if you're using IBC to bring over assets pegged from another chain, cross-chain assets, all those kinds of things, those all can be transferred uniformly. I can have a payment, and whether it's ETH pegged over from another chain or a local token, the payment architecture is the same, the process of escrowing is the same, the code that manipulates it is the same. And that's hugely simplifying across these platforms. If anyone's built contracts in something like Ethereum, where how you handle a payment in Ether and how you handle a payment in an ERC20 token are radically different. They're nothing like each other, right? Okay, so that's an intro to Zoe. I'm going to talk a little bit about the electronic rights protocol that helps, transfer protocol that helps us build this. And this is the protocol that lets us abstract in the asynchronous world across all these different transactions. So ERTP provides that foundation. Turns out it's actually pretty simple. And there's a bunch of these protocols where the hard problem is getting the right little boundary so all the pieces fit together in a bunch of scenarios. So there's a purse. That's like an account. It's a holder of digital assets, right? So it's got a balance. It's got various other properties. And I can withdraw from it a payment. So the payment is how I transfer digital assets. Currencies, concert tickets, covered calls, whatever it is. I can have a payment that contains one of those assets. A mint for one of these assets is the thing that creates them, that can instantiate a brand new one of these assets is a mint. So if it's a fungible token, I just say, give me 4 more quatlus, right? And I'm manufacturing out of whole cloth, and if I want to be able to prove that that can't happen, I take the mint authority and I throw it in a deep dark hole so no one can get at it, and now I can't create any more quatlus. And then finally, there is an assay. Well, not finally, but no one expects to span it. No, sorry. So I mentioned quatlus, I mentioned ETH, I mentioned concert tickets. Not all accounts or not all purses can contain all assets. Each kind of purse contains a particular asset. So for any particular asset type, asset kind, I don't mean asset class because that means a specific thing to finance folks, right? But for concert tickets versus quatlus, I have a collection of these things called, I have units. I don't have 400, I've got 400 quatlus, right? So I've got items that have units, and these purses and payments and mints and assays are all parameterized by those units. So I have a purse of quatlus, I have a payment of quatlus, I have a mint that will make quatlus, and I have an assay that will verify that the thing that you just presented me is in fact a thing of quatlus, is a payment of quatlus or a description of quatlus or what have you. So it's the tool that I get to use in my programmatic system to be able to plug all this together. Okay, so I need to hurry up here. So I always try to give a little bit of code, but there's only 2 pages worth. So on the left is mints and payments. So I can mint, so up there I make a mint for the concert tickets. This is on the right. I pull out the assay. Remember, it's the thing that will validate that a concert ticket is the real concert ticket, and I give it to the venue. If someone was to say, hey, I want to give you a concert ticket to go to this concert, the place you're going to want to go to, the authoritative source to authenticate that concert ticket and make sure it's real, is to go to the venue that's giving the concert and see if they're going to honor this concert ticket, right? So that's what we do. By construction, you get the assay from the place that you believe. And now I mint a seat, a seat E4. That is the units of that concert tickets are denominated in is seats, and I'll send it to Carol with received ticket and pass her a ticket, right? So now Carol receives a payment for a digital asset, which is the concert ticket of the seat E4. Okay? So now what happens on the assay side is Carol gets this. Well, what does she do with it? She just got, as far as she knows, a pointer to a ball of mud. It's just an object in a programming language. She needs to validate that she got the real thing. So the assay is the tool to do that, right? I can do assay claim all, and that does two things. It only succeeds if it actually is a concert ticket that the assay is standing behind, where the assay is the assay from the venue. If it's supposed to be Quatloos, you use the assay for Quatloos. If it's supposed to be gold, you use a careful scale and you assay the gold, right? And when she has claimed that, she also knows that not only is it valid, but that she has exclusive access. So now no one else in the world has access to this concert ticket, and we have succeeded at a commercial transfer to her of the concert ticket. Now, purses are the holder of assets. They also provide a mechanism that gives exclusive access, because underneath the covers it's actually built with an assay, which is I can take this purse, I can take this payment and just deposit it in my account where I've got a purse for concert tickets, and I deposit a payment of concert tickets, and it goes, yep, I've now got a concert ticket in my purse. You can pull it up in your UI to be able to show it to people or whatever. And then purses you can also withdraw. You can see up there with that Carol, in response to successfully claiming her concert ticket, pulls some money from her fund purse and sends it back in a reply. Now, there's lots of reasons why this is not how you would actually do commerce, but it shows the abstract mechanisms you can express in a programming language for transferring and taking ownership and being able to build interesting commerce interactions from it. In other talks, I would go forward and talk about escrows and that sort of thing. Now, I do want a reminder here, because the heart of ERTP is the assay function, that exclusive transfer is so important, is that I'm going to reiterate that it takes something that you're suspicious of, right? Something that you just got from a stranger, or maybe something you got from someone you do business with regularly, but good fences make good neighbors. And on success, it gives you back something you can rely on. It gives you back something that your trusted authority vouches for and assures that you have unique access to it. Those are huge value to be able to express in a couple of lines of code systemically for any asset representable in the program. So that means fungible assets, non-fungible assets. The whole point of having units is I can have units which are, as I said, denominated in natural numbers, at Quatloos, or I can have units that are denominated in individual items like seats in a theater, or covered calls that expire on a date or what have you. Okay, so we're close to wrapping up here. Just a little high-level concept. So first, the roadmap. Some people like. So we have a proof of concept implementation of Zoe now, and it's awesome. It's really great to be able to play with that. And there's a hackathon at the beginning of November. I say that for the internet audience. That means it's this Friday, and it actually starts in the evening, and then it goes through the weekend, where people can start building on our platform and a variety of others. And in particular, they can start to use Zoe. And you saw the wallet UI, and they can build with that and so forth. We will be updating the APIs based on what we've already learned from being able to build on it now, and from what we learned from people building on it at the hackathon and our development going forward. Adding things like modular offers. So I don't want, at the right price, I'll get 2 tickets, right? So I'm willing to make an offer for more than one item in a single offer. Disjunctions, I'll get a ticket for this seat or for that seat. So all of these kinds of more complex offers are easy to add support for. We're just, starting slow. Adding that thing I mentioned of exit safety on a crash, hugely important for actual production use. It's interesting and exciting in the technology before that. And then finally, there's some additional ERTP features that we'll be adding, like what we call a preemption hierarchy, right? I own the house, I rent it to you, I can preempt it and take the house back or something. Okay, so that's our roadmap. So, final 2 slides here. Offers affect the entire stack of doing smart contracts for any purpose as far as we can tell, right? So even the user interface to start with, the wallet interaction, the trusted path to ask the user what do they want to do, the audit trail, instead of saying, well, you threw money at this random number and you threw money at that random number, good luck with that. Instead, it's no. I authorized a transaction for a particular purpose. That's a whole lot more useful come trying to figure out what you're doing. But it also applies to pretty much everything else in the stack, right? So offer safety gives you, protects clients pervasively from the misbehavior of their smart contracts, simplifies the implementation of those smart contracts, and once we started working with it and thinking about it and designing systems and looking at systems, it really became clear that if you're going to build a growing economy of smart contracts, where contracts are building on other contracts, where I have a contract for a concert ticket, and then I can build a covered call for it, and I can sell that in an auction that then turns around, all this kind of building up an ecosystem, whether it's DeFi or connecting to the real finance system or doing freight management or any of those kinds of things that people are working on. It's hugely important that each component is safe from the next, because otherwise, without that, it's easy to end up unknowingly engineering cascading systems failures across multiple of these different fragile programs. And that's not a way to get to a successful world. And so this is, at all levels of programming, a tool to help us really bring the diverse economy that we all live in, that we all want to get, that we all want to get online, helps us bring it into the decentralized world of Web3. So, thank you very much. And questions?
So what you've described there is how to completely overhaul the current financial system in a few lines of code.
I would not be so ambitious, but...
The three elements you've described, the first of what's called a central living order book. In a financial market, I come to a market and want to buy and sell something. Secondly, what's absolutely key to Zoe is what in financial markets is called DVP, delivery versus payment. There's a bank holder in every financial market that basically says, seller, come to me with your asset. Buyer, come to me with your cash. I'm going to do some magic, and I'm going to say, when I get the cash, you can have the securities. That is a billion-dollar business. And you've described in a few lines of code how to get rid of that.
Like I said, we're excited about it.
And the final piece is what's called, and no pun intended, is finality. In a trading system, it's really important in what's called clearing and settlement to have finality. In other words, it happened, right? This thing actually happened, or it didn't. If it didn't, we all take our assets and walk away. If it did happen, it finally happened, and we can move on. It's astonishing. In a few lines of code, you basically said that a financial system that costs billions of dollars is really not necessary, not required.
Well, or this is the way you want to. This is where you want to migrate it to. There's a lot of it that's required. I mean, there's a lot of really smart people there solving hard problems that I don't solve. Right. But there's a big chunk of that like with the corporation talk earlier, a big chunk of that can be brought online and automated, can be objectified in code, and then leave the hard parts for humans to sort out. Right?
Question.
Wait. Let me. Okay. Question. Go ahead.
So, what do you think financial market participants will make of this?
Okay. So. Hand it back. So I actually think it'll be exciting, partly because of the alignment of how they think about things. One of the things when we've talked to folks out in the mainstream world, financial, freight, what have you, is again that's where some of that signal of wow, this is really low level. It doesn't quite match how we think about this stuff. And so to the folks that I've talked to, it's resonated. They go, oh, offers, duh.
So at what level of this stack is the logic that reasons about the integrity of the context? So the machines. You might have one that's a public chain that's very high integrity. You might have one that's a Raspberry Pi running in my basement. To evaluate a projection of a contract running in one of those, you have to reason about what it's coming from and how well you can trust that that process is executed correctly.
Right. So there is an answer to that, which might be longer than I can talk about here. Mostly, it's by construction. As a user, I've got a starting point for the contracts I want to talk to. My mechanism for getting to them should be reporting to me on the platform that they're on. or I'm deploying on a particular public chain and that's the services I want to go to, right? If I look for, where do I want to run my currency exchange, one of the bits of information that I'm going to get when I do a web search on that is, this is running on someone's basement. That's a DEX being run by a large financial institution that knows what they're doing. Okay, I kind of know where to go.
High integrity central hubs that all the assets get registered from, and then you can.
I think there will be multiple high integrity central hubs on multiple chains that can all provide some level of cross collaboration, cross corroboration of the quality of these different chains, and they will have different kinds of security, different levels of security be appropriate for different businesses, have different performance characteristics and so forth. The important thing is it's not. The ability to do asynchronous messaging lets the code that's doing the invocation be agnostic to that. But the party that set up that link is not agnostic to that. So I decide which exchange I'm going to talk to, and then I run an exchange front end that couldn't give a damn. Right? And so I decided it's on that high reliability thing, but I'm going to use the same polished UI, whether I'm talking to the bookie down the street, or betting in the casino in Vegas, or or off to Monaco, right? And so the construction is where you make those trust decisions. It's not something you dynamically have to worry about when software is executing. Dan.
So I see you've assembled this offer safety out of your ERTP platform.
Yes.
So let's say an application developer comes along and they say, well, I've got some market criteria that I'd like to satisfy. It's a new kind of safety that you haven't considered. How hard is it to implement and verify, let's say, a hypothetically arbitrary new kind of safety, like I'm making an auction, I want to know if I've got the top, it's a second price auction. I want to know if somebody bid more than me
right.
when I pay out. How hard is that given this platform to improve?
So one of the nice things from an ecosystem point of view is, our stack is all open source, and it's not that Zoe takes over the world. Zoe is a host of contracts that can coexist with other hosts of contracts. Indeed, we've talked about Zoe v2, where you aren't necessarily escrowing the assets themselves. You might be escrowing a covered call for the assets and the money to pay for it. So, you need to pay in Quatloos, but you have simoleons. You don't want to do the conversion unless you win. So there's lots of ability for those mechanisms to coexist, and we're very supportive of people coming up with new safety properties. There's an interesting, exciting, very cool crypto niche that I would like to see cross to the mainstream, which is 1,000x or more larger, right? And so anything that can help us get over there is a big win for all of us, and our focus is very much in that thing. So someone's got a safety property, bring it on.
We have time for one or two more questions.
Depends on how much you want to drink.
All right, so a lot of these terms seem pretty specific to order books or exchanges. So I'm curious what you see as the types of applications that it's going to be most useful for initially, and then long term, what kinds of commerce, any kind, that it's really not ever going to support, or is it every type of global commerce?
So that's a great question, and we use those terms specifically so people think with care about how the pieces all fit together. In our experience, it's not limited to those use cases. It's one where I can make an offer for the infrastructure that is going to want to charge microcents for a magic weapon in a game. There's no reason why it doesn't use the same framework. If I want to be able to buy a stack of interesting papers, I have a multiplicity of offers saying I'll pay 5 cents a paper, right? And I can do subscriptions. I can do all sorts of cooperative arrangements, because mostly this is a lot more about, in some sense, the right of contract. It's the quid pro quo piece of here's what I'll offer, here's what I want in exchange, and whether that's barter or whether that's services that an oracle will validate you performed for me, those can all be expressed and confirmed with an assay that can measure, in an oracle sense, well, did you actually perform the good, the service outside of the chain that I was actually expecting? So while there are almost certainly things that it's not well suited for, we don't have any particular list of those. We don't have any identification of those. Yes, Kate?
I can add some.
Kate implemented a bunch of this stuff here. So.
Just to answer like what is
We love it.
intended for, so anything that's just maybe a one-way payment or maybe a gift where you're giving something but you're not expecting anything in return, there's no offer safety to enforce there. So that's what it's not good for. But in terms of the range of things that it can be used for, it's pretty much any kind of commerce that you can imagine. Anything where you're offering something and getting something in exchange. So Dean presented our Uniswap implementation, AutoSwap, and in that, you might add liquidity to the liquidity pool, and you might get liquidity tokens in return. So it might not be that you're trading one asset for another type of underlying asset. It might be that you're getting, some kind of like higher abstraction right in return, and so it can get really complex.
Actually, there's an interesting point about the liquidity token for the auto swap, which is it in some sense isn't protected by offer safety because I go through the transaction, I contribute my 2 assets, I get back a liquidity token, and now that exchange is done. And now I've got this thing that represents some kind of future right on this pool, but we haven't constructed that so that it comes out as an offer as opposed to, no, it's just an asset that represents that right, and if I want to trade it back in, I go through a short-term offer. So there's some things that we haven't, there are complex arrangements that don't naturally fall into offer safety so far, but that's the kind of thing that we'll be working on more abstractions for.
But is there sort of like a lower bound in terms of economic value where the time delay or the computational cost makes this unreasonable?
Right. So the question was, is there a lower bound on economic value where the computational cost makes this unreasonable? The answer is almost certainly, but the operations are actually, just a couple of message sends in JavaScript, right? Browsers do millions of these all the time. And so the computation is actually pretty cheap for doing this stuff. One of the nice things about strong abstractions is all of that interaction doesn't require any crypto at all, right? It's strong. It's using the secure properties of the language and strong confinement to achieve strong relationships and strong trade exchanges in a very lightweight fashion. So the answer is yes, absolutely. There are high-frequency trading applications or those kinds of things that could use this. Maybe not maybe not with the current consensus algorithm and transaction rates. But architecturally, as I said, there's no fundamental reason why a few messages in an OO system won't cover most scenarios. So you can do real-time systems this way. They can pay for, in an earlier incarnation of this technology, in the 90s, we had a similar architecture that was paying for high-frequency network bandwidth on a network at the packet granularity. And so from a performance and scaling point of view, we're a long way from me having any concerns about that.
We are unfortunately out of time, but if you have, give it up for Dean.
Can I add one more thing here? I just want to add one more thing, that the venue is fabulous. I'm very happy that, yes, thank you for you guys. And thank you, Protocol Labs, for sponsoring and hosting this and making your part of this happen. It's just been a wonderful series.